The research we are diving into today, well, it might just reshape how we think about large language models improving themselves. We're looking at a paper called Multi-Agent Evolve, or MAE.
Yeah, MAE, LLM, Self-Improve through Co-Evolution. And it tackles a really core challenge in scaling AI.
So what's the absolute key takeaway here, like the first minute summary?
Okay, the big insight is this. MAE is a framework that lets a single LLM teach itself, evolve its reasoning, its general smarts, using reinforcement learning. But, and this is crucial, it does it without needing huge piles of human-labeled data or, external checks like a code interpreter.
Right, no external ground truth needed. And the mechanism, it's this idea of three agents, right?
Exactly. It spins up three roles: a proposer, a solver, and a judge, all from the same base LLM. They're locked in this loop.
Yeah.
The proposer makes tough questions. The solver tries to answer. The judge scores both, providing this internal reward signal. It's all self-contained.
A co-evolutionary dance, basically.
You got it. And the results, they tested this on Quinn 2.53b Instruct, a decent-sized model, and saw an average performance jump of about 4.5% across a bunch of reasoning and knowledge benchmarks.
Which, for anyone working on scaling these things, points to a potentially much more data-efficient way forward, maybe moving past the bottlenecks we see with RLAF and RLHF.
Definitely. Okay, so let's set the stage a bit more. Okay. MAE is really going after a fundamental problem in LLM training. We know reinforcement learning is powerful, right? Especially for skills like math or coding, where you need that reasoning boost.
Yeah, you need to go beyond just predicting the next word.
Right. And think about coding. When you train a model to code, you often have this perfect feedback loop. The Python interpreter. It tells you straight up, yes or no. Did the code run? Did it pass the tests? That's a clean, verifiable reward.
Black and white.
Exactly. But what happens when you move to fuzzier, more open-ended stuff? Like a complex reasoning, answering general knowledge questions, multi-step problems? Where's your interpreter then?
There isn't one, usually. Or getting that ground truth answer requires tons of human effort, which gets expensive and slow fast.
And that's the bottleneck MAE is designed to break. We've seen self-play work wonders in games like Go or chess, these grounded zero-sum environments. MAE is trying to bring that kind of self-improvement dynamic to the much messier open world of general knowledge and reasoning.
So it's like taking the game board away and just letting the pieces learn in the open.
Kind of, yeah. The environment becomes the model's own internal state, its own knowledge. It's a big conceptual leap.
Okay, so let's get into the architecture then, this multi-agent triad. What's really novel here is that it's one model, one LLM backbone, playing all three parts.
Yes, that's the core design. One intelligence acting as the proposer, the solver, and the judge simultaneously. It's like it's challenging itself, learning from the challenge, and grading itself all at once.
Okay, walk us through the roles. Let's start with the proposer, the challenger.
All right, the proposer's job is basically to come up with new questions. But not just any questions. It's trying to generate stuff that the current solver will find difficult. It's actively probing the solver's weaknesses.
So it needs to be smart about what to ask. It has two goals then.
Yeah, exactly. Two main objectives, driven by its reward. First, the questions need to be high quality. The judge has to think they're well-formed, answerable, not just nonsense. Second, they need to be hard for the solver, measured by how often the solver fails or scores poorly.
So it's incentivized to be a bit adversarial, to push the solver right to its limits.
That's the idea. Then you have the solver, the learner. Its role sounds simpler. Just answer the proposer's questions and do it well, accurately, with good reasoning.
Simple goal, but under constant pressure from the proposer.
Right, which is where the learning is supposed to happen. It's constantly being fed difficult problems tailored to its current ability level.
And holding it all together is the judge. This is where the no external reward part comes in. It's an internal reward model.
Yes, it acts as a generative reward model. It uses this LLM as a judge approach, which we've seen before, but they structure it carefully. It actually generates a chain of thought. They use these think tags internally to explain why it's giving a certain score before it outputs the number.
Ah, so it's not just spitting out a score, it's reasoning about the score. That adds some transparency, maybe some robustness.
Hopefully, yes.
Yeah.
It evaluates both the proposer's questions for quality and the solver's answers for correctness and reasoning. This whole internal judgment process is what replaces the need for human labels or that external interpreter.
Okay, so proposer asks, solver answers, judge scores. How does this loop actually run? Algorithm 1 in the paper.
It's a pretty tight cycle.
Yeah.
Proposer phase. Generate questions, filter them based on initial quality checks. Solver phase. Take those questions, generate answers. Judge phase. score both the questions and the answers using its rubric. And then, critically, there's a synchronized update step.
Synchronized meaning all three roles learn at the same time, even though they have different, sometimes competing goals?
Exactly. They use a technique related to reinforce plus ways, specifically something they call task relative reinforce plus day. This lets them update the single shared model based on the rewards for all three roles simultaneously. It's one model learning from this internal, multifaceted feedback.
That's quite an elegant setup. But okay, the architecture makes sense, but the incentives have to be perfectly balanced, right? Especially without an external anchor. Let's dig into section 2. The domain-agnostic self-reward design. The proposer's reward, or PELMS, sounds complicated.
It is carefully constructed. It's weighted sum of three things. First, there's re-quality. This comes straight from the judge, basically the question coherent, solvable, not just gibberish.
Makes sense. Got to filter out junk.
Second, and this is the core adversarial part, is difficulty. This is defined as 1 minus the solver's average score on that question. Right, say that again. 1 minus the solver's score. Yeah, think about it. If the solver aces the question, gets a score close to 1, the proposer's difficulty reward is near 0. If the solver completely bombs, score near 0, the proposer gets a difficulty reward near 1.
Huh. So the proposer is literally rewarded most when the solver struggles most. That's a powerful driver for creating challenging content.
It really is. It ensures the system is constantly pushing itself. There's also a small format reward just to make sure the output is tagged correctly, like question tags, so the system can parse it.
Okay, but that difficulty reward immediately flags a potential issue. If the proposer gets paid, reward-wise, for the solver failing, what stops it from just generating impossible questions, like paradoxes or questions with no real answer, just to tank the solver's score and max out its own reward? That seems like an easy way to break the system.
Absolutely. That's a critical failure mode they had to address. And that's where the judge's role becomes even more crucial, specifically through question quality filtering.
Ah, the judge steps in again.
Yes. The judge acts as a gatekeeper. A question generated by the proposer only gets added to the actual training data pool if the judge gives it a quality score of 0.7 or higher.
I see. So the proposer can't just generate garbage to maximize difficulty. The judge forces it to ask hard but fair questions. Difficult, but still high quality and solvable.
Exactly. It keeps the proposer honest. That tension between difficulty and quality is key to the stability.
Okay, that makes sense. Now, what about the solver's reward, several dollars reward? Is it simpler?
A bit simpler, yeah. It's mainly driven by the judge's score for its answer, little larger score, plus a similar format reward. But the judge's scoring here is really strict.
How strict are we talking?
They use a 1 to 10 scale. But the paper states any factual error, any logical flaw, any calculation mistake means the answer must get a score between 1 and 3, the absolute lowest tier.
Wow. Okay, so even if 95% of the reasoning is perfect, one tiny slip-up tanks the score.
That's the rule. Only answers that are completely flawless, correct, comprehensive, perfectly reasoned can get the top scores, like 8 to 10.
That's a high bar. It forces precision. No room for slightly off answers.
Right. It's trying to replicate the rigor you'd get from an external checker, but purely through this internal judging process. It prevents the model from getting lazy or developing bad habits.
Okay, so we have this intricate system of checks and balances, adversarial pushes, and strict internal grading. The big question then, does it actually work? Does it lead to stable improvement? Let's get into section 3, the empirical results.
Right, the validation. This is where it gets really interesting. They tested MAE using Quen 2.5-3b instruct. They had a few MAE setups using a seed set of about 960 questions from 14 different benchmarks, things like GSM-8K, math, human eval, BBH, tough stuff. But crucially, the MAE runs didn't get the actual answers to these seed questions.
They just used the questions as starting points or references sometimes?
Exactly. And they compared MAE against baselines, including standard supervised fine-tuning, SFT. Now, the SFT baseline did get the ground truth answers for that seed data.
Okay, so SFT had the cheat sheet, the actual answers. You'd expect it to do pretty well then.
You would, right. But here's a kicker. The SFT baseline actually lost performance compared to the original BaseQuint model. Its average score went down.
It got worse, even with the answers. How come?
The paper suggests it's likely because the seed data was so diverse, covering 14 very different domains. Standard SFT just couldn't generalize effectively across all of them, It probably overfitted to some benchmarks while suffering catastrophic forgetting on others. It tried to learn everything at once and ended up confused.
That's a fascinating result in itself. It highlights the limits of just throwing diverse data at SFT.
Totally. But MAE, even without any ground truth, significantly outperformed that at SFT baseline. Even the MAE 0 version, which started with only 16 handwritten questions and had to generate almost everything itself, did better than another baseline called AZR, especially on complex reasoning tasks.
So MAE could bootstrap itself effectively from almost nothing, but which MAE setup worked best overall?
The winner was MAE, half reference. This setup had a 50-50 chance of either generating a totally new question or using one of the seed questions as inspiration or reference. It achieved the highest overall average score, around 59.87.
So a mix was optimal. Having some grounding in existing good questions helps, but you also need that constant churn of novel, self-generated challenges.
That seems to be the takeaway. You need some reference points maybe to define the space, but the real driver of improvement, pushing the capability boundary, likely comes from the proposer constantly generating new, hard problems tailored to the solver's current edge. It needs that fresh, difficult material.
And what about training stability? RL methods can sometimes go off the rails, right? Model collapse.
That's often a big concern. But they report MAE was remarkably stable. They could train for over 250 steps with pretty consistent improvement, avoiding the kind of instability seen in some earlier self-correction or self-play methods. That quality filtering by the judge probably plays a huge role here, preventing the system from poisoning its own data pool.
Yeah, stopping the garbage in, garbage out cycle. The paper also mentioned something called the desirable difficulty effect. Sounds like something from education theory.
It is, yeah. The idea in learning, human or machine, is that you don't learn much if things are too easy, and you get overwhelmed if they're impossibly hard. The sweet spot for learning is when things are challenging but achievable.
Right. Difficult enough to make you struggle and learn, but not so difficult you just give up.
Exactly. And the paper suggests MAE naturally finds this zone.
Yeah.
The key moment in training seems to be when the proposer gets good enough to create questions that are feasible but genuinely difficult for the solver.
Because the judge stops it from making impossible ones, and the difficulty reward stops it from making easy ones.
Precisely. The whole coevolutionary dynamic seems to naturally push the difficulty into that optimal learning zone, maximizing the pressure on the solver to improve.
And the ablation studies confirmed all parts were needed.
Yep. They tried turning off the training for each role, one by one disabling proposer updates, or solver updates, or judge updates. In every case, performance dropped, sometimes by over 2.5%. It really confirms that the whole interactive loop, the competition and cooperation between all three roles, is critical. You need the challenger, the learner, and the internal critic all learning together.
Okay, so let's try and synthesize this. For you listening, the big deal with MAE is that it provides a viable path for LLMs to self-improve on general reasoning and knowledge tasks using RL, but without the massive cost and bottleneck of human data or external verifiers. It uses this clever internal ecosystem, proposer, solver, judge, all spun from one model to create its own challenges and rewards.
Right. If you're an ML engineer or researcher, this looks like a potentially much more scalable and data-efficient way to boost general capabilities, especially when you are working in domains where ground truth is hard to come by, expensive, or maybe just doesn't exist in a clean form. It's a step towards models that don't just parrot human data, but can genuinely extend their own abilities.
Which brings us to a final thought to leave you with. The entire MAE system hinges on the model itself deciding what counts as a good question and a correct answer through the judge. Now, if these models are increasingly learning via these internal self-defined standards, how do we ensure their evolving understanding of quality or correctness stays tethered to our shared verifiable reality? Is MAE creating truly general intelligence, or is it potentially building its own sophisticated, internally consistent, but perhaps ultimately detached virtual world of knowledge? Something to think about.